Welcome to Oddly Real. I'm Nem Stefanovic. We live in a modern age of electronics, computers, and automation. Machines and robots are able to perform tasks that historically have only been possible by human beings. These tasks are both computational and physical. Robots in manufacturing plants can assemble, weld, forge, and perform quality control tasks. Agricultural automation includes irrigation, sorting yields, and monitoring the fields. Military missiles use advanced navigation as well as gyroscopes and accelerometers to ensure highly accurate targeting. Robots and probes have also been sent to the far reaches of our solar system for exploration and scientific analysis. In all of these applications, these machines rely on sensors to perceive their environments. How does a machine sense a displacement, pressure, or temperature? How do we create devices to experience the real world and convey the information back to a machine? In this episode, we will conduct a broad survey of sensors. We will discuss what they are, how they work, and how they are used by machines for a useful purpose. A physical machine can be created to interact with the real world to automatically accomplish an assigned task or objective. These systems consist of sensors, controllers, and actuators. A sensor is a device that responds to physical phenomena like a temperature, displacement, or a force, and produces some kind of output like an electrical signal or physical change. An actuator is a device that influences the environment or a process. For example, an actuator could be a heater or a robotic arm. A controller is like a machine's brain, which takes the sensor readings, conducts calculations, and makes control decisions to direct the actuator actions. Typically, sensors, actuators, and the controller are arranged in a feedback loop to continuously sense the environment, decide how to respond, and command the actuators to compensate in real time. This architecture is called a closed-loop system. We're going to focus on sensors and how they work. There are far too many types of sensors to fully cover comprehensively. However, there are some very commonly used sensors that tend to appear across many different applications. We will look at some of these different kinds of sensors to give us an understanding for how sensing works in general. We will start with a class of sensors that detect linear or rotational positions or displacements. One of the simplest devices is a contact sensor. This is simply a switch, which is open or closed depending on whether the device has come into contact with something physical or not. For example, a robotic arm may have a limit to its motion around a joint. So adding a contact or limit switch could signal that it's reached its maximum displacement. Here's a simple circuit that uses a contact. When the switch is not in contact, it is open and outputs a high voltage signal. When there is a physical contact, the switch is closed and the voltage is grounded to zero. Another simple sensor for rotary or linear displacement measurements is called a potentiometer. This is a device with an adjustable component. When physically turned or altered, results in a change in internal resistance. The larger the turn, the greater the proportional change in resistance. The potentiometer can be included in a simple circuit where the changes in resistance appear as changes to a voltage, which acts as a proxy for the amount of rotation or linear displacement. Sometimes a system has to detect displacements without being in direct contact with a reference target. One way to accomplish this measurement is to use an infrared or IR sensor. This device has an infrared light source, a photoemitter, like a light-emitting diode or LED. The source is paired with an appropriate detector like a phototransistor. A phototransistor is like a switch that is controlled by light. It allows current to flow through it in proportion to its exposure to infrared light. The incident light creates electron-hole pairs, which are charge carriers, to produce a current in the semiconductor material within the phototransistor. The distance in separation between the photoemitter and the photodetector results in a proportional signal current, which is a measurement of the physical displacement. A beam breaker arrangement is even simpler, since if an object obstructs the signal between the light and the detector, the circuit will detect an abrupt change to the current. Finally, an emitter and detector pair can both be made to face the target object in the same direction from a distance. This arrangement is called a photoreflector. The amount of reflected light is detected to estimate the distance from the target. Alternatively, we can measure distances using ultrasonic sensors. This device produces an ultrasonic sound pulse that reflects back from a target to a detector. The measurement range varies from a few centimeters up to about 10 meters or so. The time between the pulse emission and its detection can be used, knowing the speed of sound, to calculate the total distance traversed. Another type of sensor to detect physical displacements is called a capacitive sensor. Capacitance is a property of a capacitor element that relates the amount of charge the capacitor can hold for a given voltage. A simple capacitor is just a pair of separated conductive plates. The capacitance is completely characterized by its physical specifications of the plate area, the plate separation distance, and its contained dielectric material. Displacements that alter the physical dimensions of the capacitor will alter its capacitance value that can be detected in a circuit. For example, applying pressure to a plate can reduce its plate separation, or a shearing of the plates will change the plate alignment, all of which can be detected. Modern cell phones and touchscreen devices also use capacitive sensors to detect touch. However, in these cases, pressure doesn't need to be applied, and instead, human skin acts to disrupt the capacitor's electric field, which can be detected. Inductance can also be used to detect nearby metal objects. A coil wrapped around a ferrous core possesses an inductance. When metal is brought near, the inductance changes, which can be detected by a resonant circuit. There are many more kinds of displacement or proximity sensors, but we'll leave it at this for our purposes. We can detect magnetic fields using the Hall effect. The Hall effect occurs when moving charges, like those in a conductor, are exposed to a magnetic field. The charges will experience a force that biases them to one side of the conductor, building up an excess of charges on that side. The opposite side of the conductor is depleted of charge. The charge difference produces an electric field and a measurable voltage. If the current is constant, the voltage becomes a measure of the magnetic field strength. The Hall effect can be used in many other practical applications. For example, a current-carrying wire produces its own magnetic field, which can be exposed to a Hall sensor. The sensor will measure the magnetic field strength, which can be used to determine the current that produced the magnetic field. Piezoelectric materials are fascinating substances that have been used in many kinds of sensors. In particular, these materials develop a charge across their surface when stretched or compressed. For example, piezoelectric crystals can be placed around a mass that would compress or stretch the crystals with abrupt applications of forces. This produces an accelerometer. Temperature measurements can be made using a thermocouple. This is created when two metal conductors are joined at a junction. When the junction is exposed to a temperature, a voltage develops across the conductor ends. This can be measured with a circuit. For example, a thermocouple made from nickel chromium and nickel aluminum alloys, when exposed to 300 degrees Celsius, produces a 12.2 millivolt output. Another kind of temperature sensor is a resistance temperature detector, or RTD. The electrical resistance of a material changes depending on its temperature. Certain metals, like platinum, have a linear relationship between their temperature and resistance. As such, there is a consistent, predictable output within a range of temperatures. The sensing element is usually in the form of a wound coil that is housed in metal or glass with the leads exposed. Pressure is measured using a variety of different methods. For example, a Borden tube is an arc tube that distends when pressure is applied within it. The tube is typically attached to an indicator, which can be a physical gauge with a dial. The gauge will provide a pressure reading. Other ways to measure pressure also include the use of bellows. a flexible beam, and a strain gauge. The strain gauge is a device that changes its electrical resistance based on stretching or compressing of the flexible beam. This resistance can be detected as a change in a voltage in a circuit. We can measure the flow of a fluid using a differential pressure flow meter. In this situation, fluid is made to pass through a narrow opening. In doing so, the pressure in front of the opening is higher than the pressure beyond the opening. This pressure difference can be measured, and the fluid flow is proportional to the square root of the value. Finally, a water level sensor can be created using a simple float that is attached to a potentiometer. If the water level changes, the float will turn or adjust a potentiometer to change its internal resistance, which can be read by a circuit. There are many more sensors and sensing techniques that can be used to measure physical phenomena. There are far too many that can be covered here. Some sensors are simple components that can be used in portable electronics projects, while others are meant for use in industrial processes that must be able to withstand extreme conditions like immense pressures or temperatures. The examples covered here are just a sample to learn a few different types of sensors and how they work. I hope you enjoyed this episode, and remember, oddly real, really interesting.